students, greetings for the day. Today we discuss in basic physics in first chapter units, dimensions and frictions. Today we discuss about dimensions, that is dimensional analysis topic. The nature of the fundamental quantities are represented by the capital letters. The fundamental unit of length is represented by capital L. The fundamental unit of mass is represented by capital M. The fundamental unit of time is represented by capital L. The fundamental unit of electric current is represented by capital I. The fundamental unit of temperature is represented by capital K. The angle is represented by theta. Amount of substance is represented by mole, MOL, mole. And thermodynamic temperature is represented by capital K, etc. So in this dimensional analysis, first we know the definition of dimensions of a physical quantity. Dimensions of a physical quantity are the powers of the fundamental units which are contained in the derived unit. And dimensional formula is an expression in which the fundamental units of length, mass, time, MLT powers are required to be raised to represent the derived physical quantity. So dimensional formula is an expression which shows the relation between fundamental units and derived units. Dimensions are the powers of the fundamental units which are required to be raised to represent the derived unit. So we know the dimensional formula of some physical quantities. Length, diameter, radius, thickness, depth, height. So all are represented by m to the power 0, l1, t to the power 0, or simply l1 or l. Next, area. Is represented as it is the product of length and breadth or side square of L into L. Length is measured in terms of length unit, breadth is also measured in terms of length unit L. So L square or m to the power 0 L square e to the power 0. Third one, volume. It is equal to the product of length, breadth into height or if we consider cube, side cube, side length into side length, that is L into L into L, or L cube, or m to the power 0, L cube t to the power 0. So in these dimensional formulas, the powers of MLT are known as dimensions of mass, length, time. So in area, dimension of length is 2. In volume, dimension of length is 3. Volume equal to L cube is the dimensional formula or dimensional equation. So area equal to L square. This is the, so dimensional formula of area is L square. Or area equal to L square means it is the dimensional equation for area. Fourth one, density. Density is the mass per unit volume. So mass m, volume is dimensional formula is L cube. So dimensional formula for density is m L to the power minus 3 t to the power 0. So in this density, dimension of mass is 1, dimension of length is minus 3, dimension of time is 0, or simply m L to the power minus 3. Next, speed or velocity. Length unit by time unit. Distance by time or displacement by time. Distance and displacements are measured in terms of length units L, time unit is t. Therefore, L t to the power minus t. L t to the power minus 1 or m to the power 0, L1 t to the power minus 1. So in speed or velocity, dimensions of mass is 0, dimension of length is 1, dimension of time is minus 1. Now we shall consider more derived quantities and we shall know the dimensional formulas. We shall derive the dimensional formulas of those derived physical quantities. Next, acceleration. Derived physical quantity, acceleration. So acceleration is the rate of change of velocity. So change in velocity by time. Change in velocity by time unit. So change in velocity or velocity is L t to the power of minus 1 by time unit t. So L t to the power minus 2. Dimensional formula of acceleration is L t to the power minus 2. Here dimension of mass is 0, dimension of length is 1, dimension of time is -2. Force. Force is the product of mass and acceleration. So its mass is represented by capital M, acceleration is derived above as L t to the power -2. So dimensional formula is mL t to the power -2. Here dimension of mass is 1, dimension of length is 1, dimension of time is -2. Next, momentum. Mass into velocity. Momentum is the product of mass and velocity. So mass unit is represented by m, velocity is t to the power -1. So ml t to the power -1. In momentum, dimension of mass is 1, dimension of length is 1, dimension of time is -1. Impulse. Impulse is the product of force and time. Force dimensional formula is ml t to the power -2 into time t. So impulse dimensional formula is ml t to the power -1. Here dimension of mass is 1, dimension of length is 1, dimension of time is -1. Work or energy. Force into displacement. Force ml t to the power -2. Displacement is measured in length unit. So dimensional formula for work or energy is ml square t to the power -2. Let us derive the dimensional formula for power. Derived physical quantity power. Power is the product of force and velocity, or work done by time. So work done by time taken. So the dimensional formula for power is ml square t to the power -3. Frequency is defined as the number of vibrations per second or number of oscillations per second number has no dimensional formula. So 1 by time t to the power minus 1. Velocity gradient also has the same dimensional formula, t to the power minus 1. And angular velocity also has the same dimensional formula. Angular velocity is defined as the rate of angular displacement, angle by time. That is 1 by t, same t to the power minus 1. The angular displacement or angle. It has no dimensions, so m to the power 0, l to the power 0, t to the power 0, dimensionless quantity. Next, pressure or strain. Let us derive the dimensional formula for pressure or stress. Force per unit area. Pressure is defined as the force per unit area. For force, dimensional formula is m to the power minus 2 L square. So dimensional formula is m L to the power minus 1 t to the power minus 2. Pressure and stress having the same dimensional formula. Next, Planck's constant. This is the dimensional constant. Energy by frequency. So for energy, we derive ml square t to the power minus 2 by frequency t to the power minus 1. So dimensional formula is ml square t to the power minus 1. Dimensional formula of latent heat. It is the heat energy required to raise the temperature of unit mass of the solid. Latent heat L square t to the power minus 2. Moment of inertia. The dimensional formula for moment of inertia is mass into radius square. Radius is measured in terms of mass length units. Therefore, dimensional formula for moment of inertia is I equal to ml square. Let us know the dimensional formula for surface tension. It is the force acting per unit length of the line drawing on the liquid surface. Force per unit length. So force ml t to the power minus 2 by length L. So dimensional formula for surface tension is mt to the power minus 2, or it may be written as m to the power 1, L to the power 0, t to the power minus 2. Or simply written as mt to the power minus 2. Next, coefficient of viscosity. ml to the power minus 1, t to the power minus 1. Next, let us derive the expression for universal gravitational constant. These are the dimensional constants. It is represented by capital G. We know that force of attraction between two bodies in this universe of masses m1 and m2, which are separated by distance d square. Then, according to Newton's universal law of gravitation, F is proportional to m1 m2, F is inversely proportional to 1 by d square, or F equal to some proportionality constant G, known as universal gravitational constant. So F equal to G into m1 m2. From this formula, G equal to force into distance square by m1, mass of the first body, mass of the second body. So force ml to the power minus 2, d square distance is measured in terms of length unit L. Mass is mass of the first body is measured in mass unit M. Second body is also measured. So dimensional formula for universal gravitational constant is m to the power minus 1 L cube T to the power minus 2. So here dimension of mass is minus 1, dimension of length is 3, dimension of time is minus 2. Next, universal, we shall derive the expression for universal gas constant, capital R. We know the equation, gas equation PV equal to RT. From that universal gas constant R is equal to pressure into volume by temperature. Pressure into volume by temperature. Pressure is force by area. Into volume by temperature. So force MLT to the power minus 2, area L square, volume L cube, temperature K. So from this expression, L square T to the power minus 2, K to the power minus 1. This is the dimensional formula for gas constant. There are so many derived physical quantities, but generally we come across with these physical quantities more frequently in our basic physics. Now, we know about the dimensional analysis applications. Before going to dimensional analysis applications, first we know principle of homogeneity of dimensions. Principle of homogeneity of dimensions states that the dimensions of all the terms on the two sides of the equation must be same. So whenever we consider derived unit in one system and the derived unit in another system, then as per this dimensional formula of a physical quantity, generally numerically having different values in the two systems, but when the unit is bigger one, numerical value must be less. So when we consider 1 kilometer, so 1 kilometer is equal to 1000 meters. So numerical value when converted into meter. So here kilometer is the bigger unit, so numerical value is less. and when the unit value is small, so this is the conversion. When converting from one unit in one system to another unit in another system, then this principle of homogeneity must be used for the conversion of units from one system to another system. If the dimensional formula is represented generally by m1 in one system, m1 to the power a, m1 to the power b, t1 to the power c, and numerical value be n1 in one system of that derived unit, and n2 be the numerical value in another system of the same derived unit, then according to the principle of homogeneity of dimensions, the powers of fundamental units on the two sides of the equation, that is the dimension of mass on the two sides of the equation must be same. Here m1 power is a, here also m2 mass power is same a. Similarly, length dimension is here b, here also b, same. Similarly, dimension of time of derived unit in one system is c. Dimension of time in another system is also, for time is second system, the dimension of time is c, same. So the dimensions or the powers of MLTs are same in the two systems, but numerical values are different. So if we know the numerical value in one system, then we will know by using this equation the numerical value in another system by using this equation. So principle of homogeneity of dimensions states that the dimensions of all the terms on the two sides of the equation must be same. Suppose if we consider the applications of dimensional method, dimensional method is used to convert one system of units into another system of units, and dimensional method is also used to check the correctness of the given equation, and the dimensional method is also used to derive the possible existing relationship between the different physical quantities involved in the derived unit. Now we shall discuss the applications of dimensional method in detail. Applications of dimensional analysis or applications of dimensional method. Both are same. System of units into another system of for example, let us convert dyne into Newton. So dyne is the unit of force. Similarly, in CGS system, Newton is the unit of force in SI system. So here The dimensional formula for force is mLT to the power minus 2. Let the CGS system must be represented by 1 suffixes, and let the dimensional formula for Newton is the same, but since it is in SI system, we use the suffix 2, M2, T2. Similarly, mLT to the power minus 1. Words are same on both sides, but numerical values N1 is equal to 1 dyne here. So 1 dyne. We does not know the value of in SI system, so N2. So we want to calculate the value of N2 from this. N2 is equal to, this is dyne, this is Newton. So N2 is equal to M1 L1 T1 to the power minus 2 pi here L1 is equal to 1. M2 L2 T2 to the power minus 2. L1 is 1. M1 is 1 centimeter. L mass is 1 gram into T1 1 second to the power minus 2. Similarly, M2 is 1 kg into 1 meter into 1 second minus 2. And 1 value is 1. So N2 is equal to, using the principle of homogeneity of dimensions, we are converting the value of dyne into Newton. So by using the principle of homogeneity of dimensions equation, N1 into so from this expression N2 is equal to 1 kg. So here we convert kg into grams. 1 cm into 1 gram into by 1 meter means here 100 centimeter into 1 kg means 1000 gram. So units gets cancelled. 1 by 10 to the power 5, that is 10, N2 is 10 to the power of 5. Therefore, 1 dyne is equal to N2. N2 means 10 to the power of 5. This is Newton. So 1 dyne is equal to 10 to the power minus 5 Newton, or 1 Newton equal to 10 to the power 5 dyne. This is the conversion method. Like this, we shall convert any unit. For example, we convert centimeters into meter as, similarly 1 meter equal to 100 centimeter, like that, or 1 kilometer equal to 1000 meters. Simple. Similarly, when we convert energy unit from CGS system to SI system, erg into joule, then 1 erg is equal to how many joule? 10 to the power minus 7 joule, or 1 joule is equal to 10 to the power 7 erg. By using this principle of homogeneity of dimensions, we convert it like this. Next, dimensional method is also used to check the correctness of the given equation. That is another advantage of this dimensional method. Second advantage, to check the a given equation or formula. For example, we shall check V equal to U plus GT is dimensionally correct or not. So we shall check the here given equation V equal to U plus GT. So left hand side is V, that is velocity. Its dimensional formula is Lt to the power minus 1 and m to the power 0. Velocity. Similarly, when we take right hand side U plus GT, here V is the final velocity, U is the initial velocity, same m to the power 0, L1 t to the power minus 1. GT should be also same, and because they are added to each other, both the terms U and GT has the same units and dimensions. So G is nothing but the acceleration due to gravity, Lt to the power minus 2 into time t. So when we multiply this, we get the same Lt to the power minus 1. This is so similarly T1 into t to the power minus 2 becomes Lt to the power minus 1. So by adding, because the same units here Lt to the power minus 1. When we comparing with the left hand side unit Lt to the power minus 1, here also same Lt to the power minus 1, m to the power 0 here, that equal to 1. So LHS equal to right hand side, same units possess on both sides. So this is dimensionally correct. So this is dimensionally correct. Third application, this dimensional method is used to derive the possible relationship existing between the different physical quantities. That is, this dimensional method is used to derive the formula existing between the different physical quantities. That is, suppose work done equal to mgh, or kinetic energy equal to half mv square, or velocity equal to root E by d, elasticity by density. So like these equations we shall derive by using the dimensional method. We shall derive these equations are t equal to 2 pi time for simple pendulum oscillations, t equal to 2 pi root L by G. So these equations are formulas are derived by using the dimensional method. So, and this dimensional method is also have some limitations. By using this dimensional method, we cannot determine the value of dimensional constants, like in t equal to 2 pi root L by g, we did not determine the value of here 2 pi, and also we are not able to determine the experimental constants also. And this dimensional method is not applicable to trigonometric functions and exponential functions. When the equation is sum of two terms, v equal to u plus at or s equal to ut plus half at square, then this dimensional method is not useful for deriving the formula. And this dimensional method is not a universal method, as it is having some advantages. We are using this method only. So thank you. If you have any doubts, please contact my number and ask me anytime.